Okay, hello to everybody. My name is Rouslan Svintsitski. So I'm sales engineer at 3D CERAM SINTO, France. And I will share with you first our process, the process of advanced ceramic 3D printing that we propose to the market. So the company, first brief introduction of the company. So company 3D CERAM started about 20 years ago, and we started our business from printing of parts, of ceramic parts, actually for biomedical field, biomedical applications, mainly implants. And over the years, we came to change our business model, and we are now process provider for this technology. So it means that we manufacture and propose our equipment, the printers, but also some post-process equipment. We develop our software to help to prepare the printing, and we prepare, manufacture, and propose to the customers the ceramic formulations for these printers. And of course, we render some dedicated services to them. It means, starting from the training of the customer, install, supervision of installation and assembly, up to the audit of the production process, co-development of the applications and parts, etc. So here are some animation of what is our core technology, SLA, called stereolithography. Stereolithography consists to print ceramic slurry, which is composed from ceramic powder and photosensitive binder. As you can see on this animation, the slurry in liquid phase, it's slightly viscous, is dispatched on the build plate by the recorder. So this recorder dispatches the slurry in very thin layers, between 25 and 100 micron, depending on the material, on the presets. And then UV laser, you can see right now, installed above the build plate, cures each layer in each location of the part. So like this, we can print several parts on the build plate with very high accuracy and quality to get high quality dense ceramics. Couple of words about our equipment. So the range of our proposed equipment is very simple. There are three sizes of printers. So the first one is C101 Easy, which is declined in two versions, lab and fab. This machine has the build plate of 100 by 100 by 150 millimeters in Z, and mostly dedicated for R&D works, education, to make prototyping, to make some small parts or small series of parts. This is actually a very user-friendly machine and is, a lot of success among universities and R&D centers all over the world. Next machine is in size is C1000 Flexmatic, which can be equipped with one or two lasers. So you understand this machine is bigger in size. Its build plate is 320 by 320 by 200, and it's dedicated mostly for the production. So once you develop your parts, you integrate this into industrial production process to make medium or large series of products or bigger parts. So this machine is equipped with some automated trolley to unload the build plate from the machine and to recycle the slurry. Very important to understand that the slurry you use, which is not polymerized, which is not cured, can be recycled up to 7 times. And finally, the biggest machine, which is the biggest in the world right now, is the machine C3600 Ultimate machine, which is able to print the parts you can see on the bottom of the screen up to 500 millimeter in print size. So its build plate is 600 by 600 by 300. So why do I speak about all these machines? So three machines, but all of them are working with the same interface, same laser, almost same slurry formulations, just to scale up, to be able to scale up and to go from the lab to fab in very easy way. So when you do some prototyping, when you do some R&D, when you do some basic fundamental research, so you can scale up if your research is successful. If you find out the right solution, right material, you can go scale up and increase the output of your machine by reducing the costing at the same time. You can see the time of printing on each machine for the same part, actually indicate in the bottom of each machine, so kind of spider part. You can print 4 parts in the same run on the small machine and up to 112 parts at the same time on the big machine. So of course, the time is in relation with the quantity in this case. So you can get from 20 minutes, you can decrease this production time to 6.4 minutes per part, which is very important, which has big impact on the costing. Materials are very important, and we will see it in a little bit later. So we could develop some materials, some standard ceramic formulations going with our machines, but we can also develop some materials on demand. So this is the service we can grant to our customers. And we also, it's very important to know that all our machines are open parameters. It means that customers can develop their own slurries, their own formulations, do not depend on us or on other suppliers for this. What are the materials we are typically working? So there is the family of oxides, non-oxides. So oxides, you know them, mainly alumina, but also zirconia, and we have 8% yttria zirconia also available, but biomedical materials like HEP or TCP or ATZ are also available, and some kind of niche materials used for some specific applications like cordyroid or silicore. From the non-oxide sides, we have aluminum nitride and silicon nitride, which are very, very interesting materials for different applications, including this one. We will see it later. As I said, our customers could develop their own slurries, and we have this experience with some of our partners from Singapore. They could develop transparent, translucent ceramics like Spinel or YAG, or other customers like Matais, who could develop ceria-doped zirconia for dental industry or for orthopedics, or other customers that could work with regolith, for example. So this is to give you the overview of the capabilities of the machine, because the ceramic materials we have in stock, we have in our portfolio today, are not really limited, do not limit the capability of the machine. Speaking about materials, it's very important to see what are the materials usually used in this application, biomedical application. So first of all, of course, zirconia, 3% yttria, because of its biomedical compatibility, but also about chemical inertness, high hardness, and excellent mechanical properties. Hydroxyapatite, which is very close to the bond constitution materials, which is also biocompatible and has excellent reactivity and good osseointegration. Actually, the first parts we could do at 3D CERAM when we started our business 20 years ago was from hydroxyapatite. Tricalcium phosphate is similar material used also for the implant, resorbable, bioresorbable material, which is also used for some biomedical applications. Dental. In dental, and I will speak about the dental orthodontics, translucent alumina start to be used for the orthodontic applications for the aesthetic reasons. If you have translucent or transparent parts, brackets in your mouth, you can increase the market segment of the people who is making correction. And also ceramic brackets, it's metal-free first, it's chemically inert, and have printed brackets have excellent mechanical properties. So they can reduce, we will see in a small study case I will present later, you can reduce the correction time by almost twice. Alumina is also biocompatible and approved material for some applications. Zirconia as well is used for dental, so I will not tell more, so I will let the next invited person to speak about. I will just review some study case here, but the purpose of this presentation is not to give you, some detailed information. We will speak dental with next person after me, but just to show you the possibility of this technology. So, for example, the first of the application was in Australia, company based in Sydney called Allegra. They could develop, they're working in healthcare sector, and known for prostheses and other orthopedic devices. and they could develop with us new materials. So in the frame of this on-demand development, they could develop with us some specific material for the spinal cages. So this strontium hardystone granite material was kind of developed together with this company to use at the cervical fusion cage. And going closer to our topic today, dental, so dental implants, dental parts, and orthodontic parts. So here are some examples of what was done, what was tested. So again, I don't want to go into this in detail. I'm not specialist of dental field, specialist of 3D printing. So the idea is here to say that additive manufacturing allows full customization in industrial level. You can print 100 parts, you can print 100 different parts at the same time. So it means you can adapt your parts for each customer. Like for the brackets, we can do each particular correction angle for each bracket and print them all together. You don't need any molds, you don't need any tools. So all your tooling is digital. And you can get with this technology, SLA technology, versus other technologies like DLP or, I don't know, binder jetting, for example. You get dense, highly high quality and high accuracy parts. Just to say that this technology was classified, was tested by independent companies, and it was, I mean, measured that SLA technology is, in terms of the accuracy, in terms of the dimensional deviation, is on the second place after subtractive technology, after machining, which is very, very interesting. And of course, as I said from the beginning, and I will resume my presentation here, that from the beginning, we targeted industrial capability. So it's not only for R&D works, it's not only for the research, it's not only for the university and education, but it has possibility to scale up and to develop your own industrial capability. So thank you very much for listening. You can note, you can write down my data. You are welcome to contact me by email, by phone. So I'm located in France. I'm in charge of North American market, but also on Middle East market. So I'm traveling a lot in Middle East countries. And you are welcome, guys, I mean, to ask any questions if you have. So I would like to introduce our partner, next speaker. Just a moment, please. Sorry. So I would like to introduce Dr. Amirali Zandinejad, who is the full-time prosthodontist at Implant Dentistry Associates in Arlington, in Texas, USA. So he completed just short biography. He completed his dental training in 1996 and continued his education by finishing multiple residency programs. He served as tenured associate professor and director of AEGD residency program in Texas A&M University School of Dentistry till 2022. He is another or co-author of more than 70 scientific manuscripts and abstracts, serves as a reviewer for scientific dental journals, and holds multiple patents on new prosthetic design using 3D printed technologies. So he lectures nationally and internationally on new technologies, 3D printing, ceramics, implant, and aesthetic dentistry. And thank you very much, Dr. Amirali. So I will let you present your presentation, which I expect very interesting. Dr. Amir, we cannot hear you.
Can you hear me now?
Yes, now it's okay.
Can you see my screen as well?
Yeah.
Okay. Is it full screen, right?
Yeah, it's full screen. It's okay.
Awesome. Thank you, Rouslan, for the nice introduction, and sorry for the gap that happened. So yes, I'm a prosthodontist, and beside my clinical work, I have been doing research on the 3D printing ceramic for almost long time now. I started to work with 3D CERAM from 2018-19, and I'm really happy to share the experiences and talk more about that fascinating technologies that I strongly believe that is going to change many things that we do in dentistry in much better way. So let's start the presentation. As the topic is already there, is the 3D printing ceramics, or zirconia mostly, in clinical dentistry. So the zirconia by itself is a very interesting material, and we have been using it for a long time now in dentistry for different reasons. One is its mechanical properties. It's really a strong material. It's biocompatible, and also because of its color. Although it's a metal, basically oxide, but it doesn't have that metallic color. It's white, or it can be infiltrated with the glass and brings different hue and color to us. So it's a very interesting material. And that's why we have been using it in dentistry for different applications, like from the single crown, a frame for the unit bridges, for the implant abutment, and also nowadays, for my job mainly is a full arch, and we use zirconia for full arch implant supported restoration, which the scientific data is very positive about that treatments. We can combine it even with titanium, having a titanium frame and zirconia suprastructure, which provides a better, maybe in some cases, longevity for us. So zirconia, it seems to be a very interesting material for clinical dentistry. The main manufacturing way for the zirconia is actually milling right now. And we have been doing that for a long time. But milling has some limitation. It consumes excessive materials. So when you have a POC and you basically mill some restoration, the rest of it is wasted and you cannot use it again. Limitation in reproducing details and complex geometries. So as I go more into the lecture, you see that some geometries and complex shapes, you cannot mill them because of a limitation of the technology, and also expenses of constantly changing the cutting tools. For example, here, we just milling few crowns, and you see that the rest of that POC may not be used for any other reason, and it's wasted. Another thing is that the details, you need a cutting instruments to be able to mill and create the shape. So we are limited by the dimension of that cutting instruments. In dentistry, as much as I know, the smallest size could be about 0.3. So anything less than this is a limitation. So we may not be able to produce those details. So nowadays, and we have another manufacturing technique that came to dentistry as well. And now we see it for the resins almost everywhere, even in the private practices, inside the offices. And it's basically now ceramic is coming up as well. So it's basically the technology, as Roslyn explained very well, it's basically adding layer by layer to get you to the final shape you want. And this is what interests me the most, because you get control over the layers, and you may become creative and do many things as the layer by layer build up. So in general, additive manufacturing has some advantages. A mass production means that you can do based on your tray size, you can use different STL file and basically fabricate your object. Reduction in manufacturing time is just one example, and that's general, not just for ceramic. I was visiting a metal 3D printing site a few months ago, and a big, for the mandible spleen, they were basically milling out of a big block of titanium. And they told me that that takes about 10 days to 2 weeks. And then they showed me a laser printing that basically they told me that it can do the same thing in 18 hours. So that's a really reduction in manufacturing time. Base material. I just heard that Roslyn said that you can use it for 7 times. Correct me if I'm wrong. Whereas when you use a puck, the rest of that puck is wasted and you cannot use it. So, but what interests me the most is the production of complex geometries. If you look at that, the skull on the right side with different, so definitely is a resin. But if you look at it, it's just I'm trying to explain the concept. So those details cannot be created with the milling. Some of them, they're so small in size that milling tools may not create it, and some of them, because of accessibility, we may not have access to all those things, 3D shape. Whereas in 3D printing, as you print it layer by layer, you get all of them. Not only you can basically create that shape, because it's a technology is there, you may be able to change the color or even the properties of each layer as it comes up. For example, the vein, the tissue, and the teeth, enamel and dentin can be printed in a different property. So it's a really interesting concept. And this is the one that I said I'm the most interested. So now consider that you are manufacturing a 3D object layer by layer, and you have the ability to change the properties, including the shape in each layer. How nice it is in dentistry. A crown that you start from intaglio, very dense, dentin kind, with the same properties and the shape, and as you get closer to the surface, like enamel, more translucent, harder. So it's very fascinating. Let's see where we are now with the ceramic. So this is just a 7 common technology that is available for the 3D printing or additive manufacturing. And some of them, they're used for ceramic. So those are, that table shows you the technologies that are available. And we actually did a review. That's a publication on the right side. It's techniques are vat polymerization, extrusion, material jetting, and powder bed fusion. To be honest with you, I tried few of them, but my main one, the one that I did all my research, is vat polymerization and mostly stereolithography, which is I use the 3D CERAM machines and slurry to do most of my research. So the technique already, Rouslan actually explained well about that. That technology give me a very good high accuracy, a good resolution, and a fairly smooth surface, which in the research that I show, that we will talk more in depth about it. So it's already gone through that, but I just show it. It's a basically 3D animation showing that you basically feed the machine with the slurry you want, and it comes on the tray. And based on the STL file, you can create dental object as well, and that include the crown or even an implant abutment, which both of them have been done. And I have some data to share with you regarding that. It could be a simple crown, and also it could be a dental abutment as well. Yeah, you see some details on that dental abutment. I come back to it because this is another interesting part during 3D printing. So as we adopt the new technology, we have to know the properties of it, making sure that whatever we deliver for our patients is good and lasts long. So let's review it quickly together. We basically did a study regarding the flexural strength and load at fracture for the 3D printing zirconia. And the study showed that it actually came a little bit better than even milled one in my study. However, there are all studies out there that showing that the 3D printing is basically bypass it, outperform the milling, or at least on the same range regarding mechanical properties. Flexural modulus is the same as well, was a little bit higher for 3D printing zirconia, but I think that if you look at the paper, as long as I remember, there are no significant differences between them. What about the accuracy of that 3D printing restorations. So accuracy in term comes with the trueness, means that how your object is close to your design STL file, and also the precision on it. As you, for example, do it 10 times, how many each time should be very close to the same result. And the combination comes as the accuracy of it. And the outcome in dentistry basically means that, okay, if something is accurate, you can nowadays look at it from with a different software. But however, one of the indication is the internal or marginal gap. So we did a study about 5 years ago, and it was the milling was outperforming the 3D printing, and the margin had some defect, but that study was done in 2018. And I was very surprised when I see the same thing with a new 3D printing crown. The data is not out there, but now completely changed over the last 5 years because of development in technology or whatever the reason is. The crown that I got in 2022 is completely different. So you see that they're equal or even outperforming even that from the milling side. So it means that you get much better a closure, internal or marginal gap. So 3D printing has to that, it's at that standard as well. So this is all about basic and bench data. What about if I really make a crown and see that if it's strong enough or not? So we did another study again a few years ago. Back, we basically picked up a crown, 3D printed a crown to be cemented on the abutment, and we compared different ceramics, including lithium disilicate, milled zirconia, and 3D printed zirconia. Actually, we couldn't find any significant differences. And that tells us that the performance of this 3D printed zirconia, the fracture resistance was equal to the milled one as well. And that study even was 5 years ago. So it seems that it's still at the same level. Since, I don't know, about maybe 20 plus years ago, bonding and adhesive plays a big role in dentistry. Anything we do, it somehow relates to that bonding, cementation, fillings, repair. So whatever ceramic, in my view, whatever we use in dentistry should be compatible, being able to bond it and use adhesive. So ceramic and mostly zirconia, most ceramics, glass ceramics, you can etch it, but zirconia, as you know, because of a crystallization and very dense crystallization, it normally doesn't have any two phases. So etching is not possible. There are different ways to get it bonded, but none of them comes to the glass ceramic yet. However, still there are ways to bond that. And if we use a 3D printing ceramic, now we have to make sure that the bond is the same as well. So we did a study regarding bonding resin cement to 3D printing zirconia. I was a little bit surprised. I thought that the 3D printed will give me more rough surface, and it came out the milled one actually giving me a little bit more surfaces, which I was surprised, which is a good thing. It means that the finishing on that 3D printing is very good. And the bonding was not that different either. However, I can tell you, because of the technology, we're working on it, the data will be out in the next 6 months. Now there are ways, because we have a control over printing, that the bonding to 3D printing zirconia will be improved drastically by not only bypassing that milled one, even maybe close to glass ceramics, which the data is out. We are going to publish it hopefully in the next 3 to 6 months. So let's go one more steps, and remember that my first part of the lecture is that where we are. We can 3D printing zirconia, but what is the property? So far, we see that it's outperformed, or at least in the same level as milled one. So implanting the aesthetic zone is a little bit challenging. And the challenge mostly comes, as you know, is not the basically white score, the tooth, because in a hand of a good technician, we can get aesthetic. Mostly it comes from the pink part. As you can see here, number seven is, I'm using the numbering from American, so it means that right lateral incisor. So it's number 7. And you see the soft tissue around it is good. Most of the problem comes when you put when you have a thin soft tissue and you put a metallic or any restoration that is not, it can discolor the soft tissue. You get a little bit bluish, grayish color around the margin. But since we have zirconia in dentistry now, that actually resolved the issue, because you can add even glass to it, which has a little bit of the translucency, and it looks a beautiful shade under soft tissue as well. So zirconia has lots of application for the implant dentistry. And mostly in the aesthetic zone, most of my cases, for the same reason, getting a beautiful soft tissue result goes to zirconia. And if we use 3D printing, zirconia, we have to make sure that it is biocompatible, and the soft tissue, including epithelial cells and fibroblasts, they really give a good response to 3D printing zirconia as well. So we check that as well. We check the soft tissue attachment to 3D printing zirconia, and to be honest with you, no differences. That means that the mill one and 3D printing zirconia, the cells attract and behaves or respond to them in almost same way. And that was the study that published as well. So now,
Dr. Amir, we lost you a little bit, your sound.
if we look at that, sorry, I didn't get your point, sorry.
No, we lost you a little bit. You jumped out, but now it's okay.
Okay, so now if we think about it, okay, everything I said, it seems that the milling and 3D printing almost at the same. So sometimes 3D printing outperform milling, sometimes didn't. But really, I am a big believer in 3D printing zirconia. But what is the reason? Very honestly, because if you show the same presentation to me up to here, I cannot tell you that why I have to go to 3D printing zirconia. But that was the first part. Let's look at the second part. What fascinates me is the potential of that 3D printing. And let's talk about now a little bit. So look at here and tell me that which one is the implant crown. Hard to say, right? But tell me right now which one is the implant crown. So it's number 8 and 9, or right and left central incisors. 2 implants close to each other. And as a dentist, we know that getting a papilla back there is a little bit different. But now, with the technology that we have in a 3D printing, can we change that? And now that interesting part of 3D printing comes to play. And maybe we can. Remember that we have a control over properties during manufacturing. We can change the things as we print layer by layer. So we looked at it in a way, and we realized that, okay, soft tissue attachment to implant abutments have different things. Abutment contour, that skill, we know about that. Abutment material, okay, we know about that. The ceramic, zirconia, and titanium, they're giving a very good result. Wettability, contact angle. But another thing is the surface roughness and porosities. That if you look at some papers, you see that with being able to customize that roughness and porosities, you may be able to get a better soft tissue result. Not only that, a better soft tissue result, maybe even the cell grows vertically coming up. So that issue that I'll show you may go away. And this is what with the milling is hard to do, if not even impossible, but 3D printing can do that. So as long as we know, which we are doing lots of research on it, we have some data out, we're giving more data out to find out that exactly roughness we want, to have it on that abutments and crowns. And then when we get to that, 3D printing can create that for us. So we can customize an implant abutment where the soft tissue is, where epithelium is, where fibroblasts will attach, and then based on that texture, our abutments. And that may give us a much better soft tissue result. So this is the crown. And just I showed that, but look at the abutments now. Abutments in that animation has some surface texture, a texture that definitely during the research that we are going to publish, we'll show you what, based on our research, what would be that porosity. But the point here is that 3D printing can create it for you on your restoration. And then that means that we come up with abutments that have a polished surface for epithelial attachment and then a rough surface and porosities for fibroblast attachment. So it grows around it. And this is the concept. And we are checking it now with different porosity, size, and everything. Data will be out soon. And it's possible, if you look at those STL files, they're very different in porosities, different size can be created and have been created with the 3D printing. And now we're testing it. And the preliminary studies so far are showing that on the resin side is showing that, yes, those porosities with a specific size can get a better soft tissue attraction and attachment over the time. And this is not just a concept, it has been created. So we just received a new abutments from 3D CERAM that I sent the STL file design, and they printed the abutments has a specific texture and porosities on part of it. And we are testing it now. Before I finish, I want to add something else too. It's another thing is that also as we basically develop this technology, other things is coming in play as well, is that we may be able to add more materials. One of the materials, and actually got my attention a few months ago, was silicon nitrate. So silicon nitrate is a very strong ceramic as well. And it seems in a different studies, mostly orthopedic studies, has a very good soft tissue attachment to it. So we started to look, and can be 3D printed. So we started to look at it, and you know that for a soft tissue attachment, wettability is very important. So we looked at it, we 3D printed the zirconia and milled zirconia and also silicon nitrate to see how it works. And it seems that the wettability is good in a range that is very ideal for the oral soft tissue attachment. And we looked at that study, as you can see here, that shows the wettability and contact angle, which is one of the indications for the soft tissue growth. The left side is milled zirconia, additively manufactured zirconia, additively manufactured silicon nitrate, and also titanium. So they are all in a good range. However, when we looked at it over the time, it seems that oral fibroblast actually has an attraction to additively manufactured zirconia and additively manufactured silicon nitrate. That publication is almost done. It will be submitted very soon. So that is a very good result for us, because that shows that we have a material. It's not just zirconia, that 3D printing can print different materials, that some of them has lots of potential in our field, in medical or dental field as well. So by having said that, I almost finished my presentation. If you are new to that technology, a new supplement just came out from that B and some of our friends. It's Dr. Irena Saylor, editor-in-chief for that journal, and me and one of my colleagues, we basically put lots of papers on that, including a review on 3D printing ceramics if you are new to that technology. So you can really go back and see that what in the 3D printing field has been done, where the research is, and also nice reviews on that can basically keep you bring you up to date to from a start where we are, and then some research studies. Almost has a 33 papers on that. So by saying that, I finished my presentation, and there is time for if you have any question. This is my information. If you feel any question, if you want to collaborate any research, this is the field that I really love, and I think that the future of dentistry is in that. It's one of the fields obviously AI, other things as well, but 3D printing is one of them, which 3D printing ceramic is very new, and I think that it will change many things that we do in conventional dentistry. So by saying that, my presentation is over. So any question?
Thank you very much, Dr. Amir. It was really very interesting. So Bassam, I like you continue maybe the animation of this webinar. And of course, all the participants who are here. So the main interest of this presentation also will be to record. It is recorded and will be registered in the YouTube channel. So Bassam will send us the link so we can dispatch to the people who couldn't assist this webinar. So yeah, please ask if somebody has some questions. You can ask in the chat or yeah.
Should I stop stop sharing, right?
Yeah, it's